Oh, I didn't see you there. No, just kidding. Anyway, yeah, everyone, welcome back. Welcome back to the podcast. Taking a bit of a break from Einstein, my boy, talking about something a bit different. So this podcast is going to be about primarily computation in the brain. So I think it's a topic that has a lot of stuff going on. So I am going to make multiple videos for it. But at least for the first one, I just want to talk about kind of the modern the modern state of thought around human beings and human beings as they relate to computing. So I think I'm going to start off talking about how computers even work. So for the most part, you probably have heard that there are things called programming languages. So there's programming languages. You've probably heard about binary, so zeros and ones. You probably have heard of some very large computer companies like Samsung and Apple and Google. And so you've probably heard that, oh, computers, they compute stuff, and then it's all zeros and ones and blah 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 blah. So I think I want to give a very concrete example of what computing is, and then start talking about kind of historical thinkers about what they thought about human beings and computing. The first thing to say is, you know, computers and human beings are quite evidently very different. We are biological things. If you use a butter knife and you try to cut up your computer, I mean, you're going to find it a hard time, especially if it's made out of metal. But if you cut a human being, like, I'm going to start bleeding, right? So quite clearly, like, I am a biological entity and a computer is not a biological entity. So that's a very big difference. Another big difference is, we've all shut down a computer or restarted it. I mean, there's no shutting down or restarting a human being. I mean, if you shut your brain off, like literally shut it off, you're gonna die. And the same thing happens if you restart it. There's no. I'm sure quite a few people want to restart the brain, restart their memory, restart everything. But you cannot do that. You cannot just restart yourself and get a fresh copy of yourself. So that's just not possible. So shut down and free, and that. Now the sleep functionality is something that we do have. So the sleep functionality of a computer is something that we do actually have, but we do not have what a computer has exactly. Another thing is, if you took a storage from your MacBook Pro and put it in another model of the same MacBook Pro, and you watch a YouTube video and you put it in, you'll see that that other computer doesn't start rejecting it, because it's like, oh no, my immune cells have now attacked my storage. That quite clearly does not happen. I mean, maybe there's some firmware issues, but you don't hear of MacBook Pros rejecting organ transplants of components. If you try to take RAM from one computer and you put in another, it's the same thing. Similarly, if you take, again, like using the analogy of storage, which might be considered the memories of a computer that it has, if you put that into another computer that's compatible, you should reasonably expect it to work. Whereas my memories are stored in my brain, and I can't just go in there with a blade and chop off my brain stem, put my brain into another person, and then reattach it, and then say, oh, let's see what happens to all of his memories. Are they still in this person? I mean, that is quite clearly insane and probably not ever going to happen. So this idea of humans and computers being the exact same thing pretty much doesn't hold any weight. Now, you might ask the question, is there at least one way that they're the same? Is there some way that they're the same? And yes, there is a way they're the same. This idea has to do with the representation of computing. So you've heard computers are zeros and ones. You've heard that computers compute things, hence their name. You know that humans essentially do the very same thing. We compute things, and you've heard, you've probably heard of, the universe is made of information, and yada, yada, yada. So I think it's important to understand what exactly we mean by zeros and ones. And for me, at least, it doesn't really make any sense until I actually researched what that even means. Because, I don't see any zeros and ones on my computer. I mean, if you look very, very hard. You're not going to find them anywhere. But I think I came up with a good analogy maybe to describe it a little bit. So you've heard of things like Python. You've heard of programming languages, right? Okay. So you code in Python. And essentially what happens is you code in Python because Python is easy for a human being like yourself to understand. We write functions and we write all these different things that have very good human meanings to them. Like, for example, you might write a function that's called save, and save does exactly what you think it does. It takes a file or something and it saves a copy of it, and then you can, it's a Word document and you can access it later on. Or you write a function called delete, and it does exactly what you think it does. It takes the file and it completely removes it from your computer. So that to you is very intuitive. These are what you call high-level programming languages. But anyway, not important. So the best way I think to think about it is think of an apartment building that has a basement. Now, human beings, when you're doing coding and stuff, typically speaking, if it was a 5-story building, Python, you would say, is on the 5th story. It's about as high as you can get. It's about as far away from the actual zeros and ones of a computer as you can get. Now, you code stuff in Python, and let's say you want to run this code. You want it to do something. So what happens is people, these ingenious people, found a way that you could walk from the 5th floor to the 4th floor to the 3rd floor to the 2nd floor to the 1st floor, and then go to the basement where it gets executed, where it's the zeros and ones. The zeros and ones live in the basement, but the languages that people use, developers, programmers, what they use is on the 5th floor. I mean, you can get further down, so sometimes people can write in assembly language, and essentially assembly language would be on the 1st floor. So the floors in between I'm not going to focus on. Those are languages like C++, these kind of C, more primitive. But from the 1st floor would be called assembly language. And what does assembly language do? So assembly language is another programming language, but it is much, much more obscure. It's completely more obscure, and it's less about. It's kind of like a subjective thing, but it's less adept to being understood by humans. It's very, very much easier for a machine to read, and I think this is another thing I forgot to mention. But human readable. The reason we invent things like Python is that we don't have to use programming languages that are easier for machines to understand. So what I mean by this is like Python in and of itself, or any of these kind of like R or Julia or Java, like these are all languages, but they're a bit, they're significantly easier for us to understand. But like, how do you go from writing print hello world in Python to a zeros and ones? How do you actually do that? And so Python would be hard for a computer to understand. But essentially what happens is that chunk of code that you run gets converted into something that to the 4th floor, you walk down a flight and it's like, oh, it's a little bit easier for the machine to understand, but but it's still much easier for a human being to understand. And then you flip down, you go to the 3rd floor, you go down the staircase again, and now you're on the 3rd floor, and it is a bit easier for the machine to read, but not quite. It's a bit harder for the human to read, but it's easier for a human being to read than a machine. Next, you go to the 2nd floor. The 2nd floor is, again, easier for the machine to read, a bit easier, but it's still, easier overall for a human being to understand. Now, once you're coming to the 1st floor, to assembly language, this is essentially where a machine says, finally, this is something that I can really work with. This is something that's much easier for me to understand and interpret what you're trying to say when you wrote on the 5th floor, hello world. Much easier for me to understand now. Thank you for, making it, dumbing it down. You can think of it that way, to my level, walking down to my level. And so once you've hit the assembly, now you realize as a human being, you're like, oh my goodness, this is so much harder for me to understand. But that is essentially kind of, there's different levels to this abstraction. And so at the end of the day, it goes into assembly language, and then assembly language turns it into zeros and ones. Now, what do you do with the zeros and ones? What does a computer do with the 0 and 1? Great question. So in your computer, there is many things that you can essentially just call as circuits. So circuits, they carry electricity, and that's about all you need to know. Now, there's another thing called a transistor. So what does a transistor do? Great question. And this is kind of where the magic of the computer comes in. So just think about one circuit. Now, one circuit carries electricity, right? Okay. So there's different kinds of transistors, but essentially what the transistor's job is to do is to monitor this one circuit that it's been given, and then it monitors how much electricity flows through that one circuit. Now, it sets a threshold for every one of these transistor manufacturers. They set a certain threshold that this transistor will become activated at. And what does this mean? It means that this circuit, when it's below a certain level of electricity coming through, a certain level of current, it's a zero. It's off. This is this idea. So this is where the zeros and ones come in. So being in the off state means that you do not, this one circuit would be a zero, represented as a zero, if it does not have enough electricity to pass this threshold. Now, once the transistor detects, yes, now you are finally above the threshold, it now understands, oh, you're on. And it flips that 0 to a 1. And so when assembly language takes your Python print, hello world, and it brings it all the way down the staircases, and then it brings it down to the main floor, and then it says, oh, I need to, feed it to a machine. What the machine does is it will start allocating this, and it will start computing things using these different circuits, and it does this using the zeros and ones. Now, that's very cool and all, but how does this help solve our problem that humans are biological entities and then machines are, made of aluminum, they're made of all kinds of different things, plastic? It's this idea of information. So if we can make an equivalency, sorry, just one second. If we can make an equivalency between zeros and ones on a computer and how human beings process information, if we can make some kind of equivalency between those two things, then we've solved it. Then we can say that, yes, a human being is really just a super, mega computer, and it has all these neurons that do all these wonderful things. But at the end of the day, it's also operating with zeros and ones. It's also doing the same thing, turning this on, turning this off, doing all these different things. Sorry, one second. Production. And so, if you can make that equivalency between the zeros and ones of a computer that it uses, and then if you can represent that in a brain, the zeros and ones, then what you have are the same thing. They are the same thing, because at the level of computing things, it's all zeros and ones. And once you get to that level of it all being zeros and ones, it's all the same now. So this idea is very beautiful. It's very powerful, and you can actually carry it a step further. You can actually go and say, well, now that we know, this is zeros and ones, what if the universe itself is a computation of some kind? The universe itself is a 0 and 1. The universe itself, in every single point in space that you can view, is a 0 and 1. What if that was true? And I will explore that in my next video. But for this video, I'm not focusing on that. Sorry, anyway, getting a bit sidetracked. So anyway, if we can build that zeros and ones of computers are the same as brains, then we have this equivalency. And so this is a lot of where the historical development of computers kind of resided. And I'm just going to talk a bit about the history, and then I'll finish off the video. But essentially, you've heard of Alan Turing. Alan Turing was a very famous computer scientist, and a mathematician actually, and he wrote a paper on something called the halting problem. So the halting problem was a famous problem that was outlined in 1900 by someone named David Hilbert, and David Hilbert had the halting problem as one of these 25 math problems that should be solved in the next century, in the 20th century. Now, the main thing to mention here is that the halting problem had to do with this idea of computability. It had this idea of, given some statement, could you determine if it was true or false? This idea, again, this is kind of like, you can think of it as being on and off. It's a binary thing. It's a 0 or 1. You can think of 0 being not true and 1 being true. Now he asked, given any kind of statement that you could provide to a computer, some kind of computing agent, would it be able to determine in a non-infinite amount of time, meaning at some point it's going to stop. One second. And it turns out that it's not true. It means that there are statements out there that if you gave it to a computer, what is called a Turing machine, in his paper, but if you give it to one of these Turing machines, which is essentially just an agent to compute if something is true or false, there are statements that do actually take an infinite amount of time, and they're called undecidable, meaning that you cannot decide if it's true or false. And so he became very famous for that paper because it essentially showed kind of a limit of computation, a limit of what computers are able to do. Now, everything that computers do are finite, so it doesn't actually really matter per se. I mean, it's about machines taking an infinite amount of time. But the Imitation Game, the movie, actually shows a really nice example of this. You notice that Alan Turing, when he builds this machine of all these rotors, he actually they find difficulty because it's taking too long to find the Enigma settings. But as soon as he makes this kind of change to it, the Enigma settings stop, and they provide him with a what the correct settings were of the day. And so his machine was able to compute these things and do this kind of task, which is quite remarkable. But anyway, going back to the question, and I mean, I guess going back, to Turing's time, when they were doing computing and stuff, he also wrote a paper called Imitation Game, which is this idea of if you had a human being sitting there and it had two kind of respondents, and they would ask questions and it would see responses from these people. One would be a computer and then one would be a human being. And it's essentially a test of saying, well, would you be able to, for the most part, determine if the responses came from a machine or if it came from a person? And so this has been an interesting thought experiment, and really why the movie was called Imitation Game, because it really distills what computing is. Computing at the end of the day, especially now with the areas of artificial intelligence, is kind of a method of replicating what human beings do, albeit clearly not in the same way as them being biological entities. But it is the question of, can you create a brain that is not biological, but is just using zeros and ones and electric currents? And so that's been a very interesting area of research, and that is kind of where a lot of this, interest in AI comes from. This idea that given enough compute, given enough resources to do computing with, given enough data, is it possible to create a human being, create a sentient being that lives on a flash drive? Is it possible? Is it something you can do? Can you deploy this thing across the world? Can it live on a server in New Delhi? What is possible once you reach that kind of stage? And is a human being's intelligence, all these different things we do so exquisitely well, is it possible for a machine to do the same thing? And I happen to believe yes. I think it is possible to do. And it's kind of for the main reason that there's already, millions of tasks that computers do substantially better than we do. And these all have to do with computability, computing things. And it might just be the case that the way we compute things with our brain, you can think about it as this kind of multi-threaded process where we're doing, a very large amount of operations at the same time for processing visual data, for processing many different things. But it seems to be the case that computers do many things that we do, but just much, much better, especially multiplication and addition, all these things. But at the end of the day, if everything is a 0 and 1, if everything comes down to this fundamental unit of computation being represented that way, it's entirely plausible to think that the universe is built out of information that can be represented as zeros and ones. It's entirely reasonable to think that we could one day build a machine that can, replicate what a human being does. These are all, totally possible things, and we're well on the way to getting there. And it is a very interesting prospect. And I think for the next video, I'm going to try and talk a bit more in more detail about kind of what new areas, like what is AI, for example. I'm going to talk about what is AI from specifically from a mathematical perspective, talk about quantum computing, talk about how the universe could be actually an emergent thing from quantum information theory. Very interesting idea there. So using zeros and ones to essentially build this huge entangled state that represents our universe at all points in time. Very cool. So there's definitely other things I want to talk about, but I hope I've made it clear that thinking about the brain and intelligence, at least one aspect of it has to be that it's probably possible to build a brain on a machine. And, this has just been a very short video for such a long topic, but I'm hoping to, add more and more to it as, as the weeks go on. But anyway, if you made it this far, thank you for tuning in, and I'll catch you next time. Thank you very much. Bye-bye.